Okay, so we're looking at the 10th FRQ practice. You're given a function, you're given a domain that it's over 0 to 8. That function is a rate of change. It's tons per hour that gravel is arriving. You already have 500 tons at the plant. It's processing at 100 tons per hour. So the first question is what is G prime of 5? That's literally a calculator problem. G prime of 5 is something you can put into the calculator. It's going to tell you that that is 24.587, and that's tons per hour per hour. So you can write that as tons per hour squared. This means that, this is part A, the rate at which gravel, unprocessed gravel, is arriving is decreasing by 24.587 tons per hour at time t equals 5 hours. Alright, so that's not so bad. Part B, also something that is eminently calculatorable, if that's a word. Once the total amount of unprocessed gravel that has arrived during the workday goes from 0 to 8. So this is integral from 0 to 8 of g of t dt, which works out to be approximately 825.551 tons. Part C simply wants to know if the amount arriving is increasing, or if the amount of unprocessed gravel at the plant is increasing or decreasing. So what we need to do is we have to say this is the rate at which things are arriving at time 5. We subtract 100 from that. In the end, that comes out as negative 1.859, which means that the amount of gravel there, since that's less than 0, the amount of unprocessed gravel is decreasing. Alright, so let's look for D. Alright, part D says what is the maximum amount of unprocessed gravel at the plant during the hours of operation. So the amount of gravel that's at the plant is the 500, right? Plus how much arrives, right? So that's going to be G of T minus the amount that's being processed each hour, dt. Okay, so we want to know when is this, sorry, that's not correct. We want to know the derivative of that, right? So the derivative of that, well, this is a constant, right? Fundamental theorem of calculus gets me that this is g of x minus 100, right? So when does that equal 0? You use the calculator to figure that out. That happens when x is approximately 4.9234803. So you only have 3 critical points here. You have the amount at time 0, the amount at 4.9234803, and the amount at time 8. We know the amount at time 0 is 500. We throw this value into this, and the calculator gets us back 635.376. And at time 8, you throw the 8 in here, and you're going to get back 525.551. That means this is the maximum. So the maximum amount of unprocessed gravel is going to be 635.376 tons. All right, so looking at problem 2, this is one where you're given a table of data points. We're dripping coffee into a coffee cup. Use the data in the table to get C prime of 3.5. So for that one, we don't have 3.5 as a data point, so we're going to approximate C prime of 3.5 using 3 and 4. So C of 4 minus C of 3 over 4 minus 3. That's 12.8 minus 11.2 over 1, which means that about 1.6 ounces per minute that the coffee is pouring into the cup. Part B needs you to read between the lines a little bit. It says, is there a time between 2 and 4 where the derivative is 2? Okay, so MVT says that there exists C on the interval 2 to 4, which is differentiable, right? Where f prime of C has to equal C of 4 minus C of 2 over 4 minus 2. C of 4 is 12.8. C of 2 is 8.8. That's 2, and lo and behold, that equals 2, which is the number that we're looking for. That's a mean value theorem problem. So let's move on to part C. All right, so looking at part C, use the midpoint sum of 3 subintervals of equal length to indicate the data from the table that approximates 1/6 of 0 to 6 of C of t dt. So this is going to be 1/6, approximately 1/6. The first interval is, the midpoint is 5.3 times 2. The second interval's midpoint is 11.2 times 2. The third interval's midpoint is 13.8 times 2. So this is 1/6 times 10.6 plus 22.4 plus, this is 13.8. So that's going to be 27.6, which gives you 60.6 over 6, which is 10.1. So this means that the average amount of coffee in the cup is approximately 10.1 ounces on over the interval from t equals 0 to t equals 6 minutes. All right, so we got part D to go in this. All right, so let's look at part D. Part D, the amount of coffee in the cup in ounces is modeled by this B now. Using this model, find the rate at which the coffee in the cup is changing at time t5. So literally, we need the derivative at time t5. So B of x is 16 minus 16 e to the negative 0.4. It should be t's t. So B prime of t is going to be, let's see, that's going to be positive. That'll be 6.4 e to the negative 0.4 t. If I take B prime of 5, that's 6.4 e to the 0.4 times 5 is negative 2. So you could literally write this as 6.4 over e squared, and that's ounces per minute. So there you go. That's problem 2. Let's move on to number 3. Okay, problem 3. Here they give you a graph of the derivative, and they give you all the areas under the curve, so that kind of helps a bit. So the first question here is asking for the local minimum, for which the function has a local minimum. So if you take a look here, the only place that we go from decreasing to increasing, or the derivative being negative to positive, is actually at x equals 6. Because f prime of x is less than 0 on 4, 6, and f prime of x is greater than 0 on 6, 8, which means that I have a local min at x equals 6. All right, so part B of this problem is a little bit more intensive, so let's take a look at that. All right, so we know that the only local minimum from part A is at 6. So the three things we have to check are the values when x is 0, x is 6, and x is 8. Okay, we know from the problem that f of 8 is 4, so we have one of them. We can use the fundamental theorem of calculus to get the ones for 0 and 6 from that. The integral from 0 to 8 of f prime of x dx should be f of 8 minus f of 0. If you add up the areas under the curve from 0 to 8, you're going to get 2 plus 6 minus 3 plus 7. This is 4. So the sum of this is 12. So f of 0 has to be negative 8. Okay, so the other one that we can try is f of 6. So we want to take the integral from 0 to 6, or no, not 0 to 6. We don't know 0. Oh, we do know 0, but 6 to 8, right? Of f prime of x dx is f of 8 minus f of 6. This is a really easy one because there's only one piece of the curve there, which measures 7. F of 8 is 4. We don't know f of 6, so this just tells me that f of 6 is negative 3. So out of 4, negative 8, negative 3, that's our minimum. So the absolute minimum of f is negative 8. So that completes part B of that problem. Let's move on to parts C and D. Okay, so part C of the problem says on what interval are we both concave down and increasing? Well, the derivative is bigger than 0. It's positive on 0, 1, 1, 4, and 6, 8. The second derivative is less than 0, so I'll be concave down on 0, 1, and 3, 5. So f prime is decreasing on these two intervals, which means that f is concave down, which means I am increasing and concave down. Well, they both include 0, 1. And then from 3 to 4 is the other interval where I'm both increasing and concave down. So that's part C. Let's look at part D. Part D is a chain rule problem. We're given that g of x is equal to f of x cubed. So g prime of x is going to be 3f of x squared times f prime of x, right? That's chain rule. So if I want g prime of 3, the slope of the tangent line at 3, I'm going to get 3 times f of 3 squared times f prime of 3. F of 3 is given in the problem as negative 5 halves square. F prime of 3, you could read from the graph, is 4. So this is 3 times 25 over 4 times 4. gives me 75. All right, so that's problem 3. So let's do problem 4. All right, so problem 4 has a differential equation at the top there with an initial value at f0 equals 1 or is equal to -1. We want a limit. So if you're not thinking L'Hopital's rule, you have not been around in this class long enough. All right, so the limit as x approaches 0 of f of x plus 1 over the sine of x. When you put the 0 in there, we get f of 0 plus 1 over 0. F of 0, according to the problem, is -1, so this is going to give me 0 over 0, which allows me to apply L'Hopital's rule. So at the limit as x approaches 0, the derivative of the top is just f prime of x. Derivative of the sine is the cosine. So I need f prime of 0 over 1. And f prime of 0, well, let's say it's going to be -1 squared, because y, when x is 0, is -1, times 2 times 0 plus 2 over 1, which works out to be 2. So there's my limit. Part B uses the differential equation in place for Euler's rule. The starting point is 0, -1. That's my initial value, right? I'm going to do this in 2 steps to get to a half. So the first step has to be a quarter. Step size is 1/4 here. So we're starting at -1. We're taking a step of 1/4. And then we want the derivative when x is 0 and y is -1. Well, we just calculated that up here. That's 2. So this is -1 plus a half, which means that first step is -1/2. X sub 2 makes the second step to a half. Y sub 2 says start at -1/2. Add the step size of 1/4. So let's see, we're going to take y squared, which is going to make that a 1/4, times 2x, which makes that a half, minus 2, plus 2, which 2 is the same as 4/2, right? So this is -1/2 plus a 1/4 times a 1/4 plus times 5/2, which is -1/2 plus a 1/4 times 5/8. Let's see, so this is going to be -16 30-seconds plus 5 30-seconds gives me -11 over 32. Final answer by Euler's method. Okay, so let's look at part C. So part C is solve the find the solution to the differential equation in using the initial value, right? So we have dy dx is y squared times 2x plus 2. This is separable. So we can integrate, take the antiderivative of both sides. That's going to give me -1 over y. It's going to give me x squared plus 2x plus c. Put the initial value in. So this is just going to be, 1. And putting zeros in there is going to give me c is 1. So I have -1 over y is x squared plus 2x plus 1. Which means that y is going to be 1 over x squared plus 2x plus 1. I have to handle that negative. This is going to elicit a domain restriction. That's factorable. It's x plus 1 squared, which means that this cannot exist when x is -1. So this is the solution. When I go through that initial value, this is going to give me this derivative, but the function is not continuous when x is -1. All right, so let's look at number 5. All right, problem number 5 is a Taylor polynomial problem. We're given some data here. We're centered at 0. We know that f of 0 is -4. We know that the first degree polynomial at 1/2 is -3. We want to know the first derivative. Okay, so it's a great problem. So the first degree Taylor polynomial at x is going to be f of 0 plus f prime of 0 times x. So we know that at 1/2 this is -3. We know that f of 0 is -4. We know that we're taking this at 1/2, right? So add the 4 to both sides. Multiply by 2 tells me that f prime of 0 is 2. All right, so that moves me on to part B. We get more data. We get the second derivative is -2/3, and the third derivative is 1/3. So we now want the third degree Taylor polynomial. So remember that this is f of 0 plus f prime of 0 x, f double prime of 0 over 2x squared plus f triple prime of 0 over 6 times x cubed. All right, so this we're told is -4. We just figured out that this is 2. We're given that this is -2/3, so that's going to be -1/3 x squared. And then we're told that this is 1/3, so this is going to be 1 over 18 x cubed. So there's the third degree Taylor polynomial. And then we've got part C. All right, so we're told that h prime of x is f of 2x. So we're going to approximate that with the polynomial. So that means it's -4 plus 2 times 2x minus 1/3 times 4x squared plus 18 times 1 over 18 times 9x. No, not 9. 2 cubed is 8x cubed plus more. All right, so let's simplify a little. All right, so that being said, the third degree Taylor polynomial for h is going to be the antiderivative of this the x. Don't think, yeah, don't actually need this term, so let's get rid of that. To get the third degree, I only need the first several terms. So this is going to be -4x plus 2x squared minus 4x cubed. And no, that's a trick. That's going to be 4/9 x cubed plus c. We know that this is 7 when everything else is 0, so c has to be 7. H cubed of x then is 7 minus 4x plus 2x squared minus 4/9 x cubed. And that's the third degree Taylor polynomial. That's the whole set. If you have questions, make sure you make it to one of the drop-ins or send me an email. Hope this is helpful. This is 10, and the test is coming. All right, thank you.